Liftoff. Burn 3. Hover. Today, I want to show you the progress of a simulation project I've been building. It is a rocket simulation I want to use as a test environment to experiment with ideas around intelligent systems, especially RAG. A big part of what motivated this project is that RAG is usually introduced through a very standard pipeline: gather data, clean it up, chunk it, embed it, retrieve what looks relevant, and pass that to the model. And that approach is valid, it is useful, and it solves a lot of important problems. But I became interested in everything outside that default picture, because once a system has a state, timing pressure, urgency, and different confident requirements, the design space gets much bigger. Not every command should be treated the same way. Some requests can afford a little more time, some can afford a little more uncertainty, but some are critical. If the rocket is falling, and I ask for a recovery action, this is not just another query. That needs to happen fast, and it probably needs to follow a very specific policy. That is really the direction of this project. So for me, this simulation is a sandbox where I can experiment retrieval, certainty, urgency, and policy decisions in a more dynamic environment. What I have today is not that RAG system yet. What I have today is a working foundation. At this stage, I already have a real simulation, learned control behaviors, and a voice interface that let me interact with the system quickly. The voice commands are not RAG-based yet, they are strictly matched commands. So I want to be very clear about that right now. The system is not doing retrieval-driven language understanding, it is not selecting policies from a language layer yet, and it is not reasoning over a knowledge base. But it is already interactive, already fast, and already connected to a real control loop. That is what I want to show you in this video, the foundation that exists now, and the direction that is moving toward. So let me show you what the system can already do. What you are seeing here today is not a canned animation, it is a real physics-driven simulation running in Bullet. The rocket is modeled as a rigid body. It has legs, a main engine, gimbal control, engine spool behavior, and finite fuel. It also senses the environment continuously using raycasts. It looks below itself, around itself horizontally, and across several directional banks in the rocket frame. So in practical terms, the rocket is constantly building a structured sense of where the ground and nearby geometry are relative to its body. That information gets packed into a fixed observation, things like velocity, attitude, altitude relative to the task, gimbal and spool state, ray hit, fuel fraction, leg state, and ground contact all became part of the controller input. Then the controller output continues the action: throttle, pitch, yaw, roll, leg-related control, and attitude corrections. So this is a real control loop. At the moment, I have 3 trained behaviors in the system: hover, land, and dive. Hover tries to hold a target altitude. Land performs a full descent and tries to achieve a soft touchdown on the legs. Dive handles a more aggressive approach profile, and then, when the right conditions are met, it hands off the landing policy for the final flare near the ground. In some situations, there are scripted assists blended with the learned controls of recovery stays stable close to the surface. That part matters to me, because I'm not interested in pretending the system is magical. I'm interested in building something that is robust enough to be useful inside the simulation. I'm going to let these runs play for a moment, because part of the point here is simply to watch the controller work. Under the hood, the behaviors are trained through reinforcement learning. During training, Python drives the same C++ environment through a binding layer, so the observations, rewards, and termination rules are aligned with what the runtime controller will actually see later. That means I am not training in one world and demoing in another. The policy that runs the application sees the same structure as it was trained on, and the graphical interface is not loading PyTorch. The trained behaviors are exported into the native application and run directly in C++ as a small tanh MLPs. For example, the landing controller reads 42 observations, passes them through 3 hidden layers of 128 units, and produces 8 continuous actions. So each control tick, the simulation is doing a native forward pass and applying those outputs directly to the rocket. That keeps the runtime simple, fast, and very close to the kind of execution path I care about. It also means I have to be disciplined. If I change the ray layout, the observation dimensions, the normalizations, or the network width, the training side and the runtime side have to stay in sync. On top of that, I can talk to the simulation. And this is where I want to be honest again. The voice layer is currently based on a strict commands matching, not RAG. So when I speak to it, I'm using predefined commands patterns. That may sound simple, but for this stage of the project it's actually useful because it gives me a fast and reliable interaction path. I can change behavior quickly, I can trigger actions quickly, I keep the demo responsive, and that speed matters. Because one of the questions behind this project is exactly that. How do you keep intelligence in the loop without making critical interaction too slow? Right now, the answer is a direct command path. Later, I want that interaction to become much smarter without losing the speed that matters in urgent situations. Today, I also introduced a moon gravity option. And one thing I found really interesting is that I did not need to retrain the controller for it. The policy train under Earth gravity transfers surprisingly well to the moon gravity. In fact, it feels safer there, because the environment is less constrained. The rocket has more time to react, the descent is more forgiving, and the controller has a little more time to find the stability. I don't take that as a proof that the problem is solved, but I do take as a good sign that the learned behavior is not just memorizing one extremely narrow case. It suggests that there is some robustness there, and I think that is worth showing. Liftoff. Burn 3. Hover. Follow. Camera ground. Land. Stop. Reset. Burn 3. Gravity moon. Land. Stop. Gravity Earth. Gravity 0. Burn 1. Land. Gravity Earth. Follow. Stop. Cool. The part I'm most interested in is what comes next. The next version is not just about taking this simulation and attaching a generic rack stack to it. What I want is a system that can treat different requests differently. Some requests might be allowed to take a slower retrieval path. Some might need higher certainty. Some might need to gather live information about the state of the rocket before deciding how to respond. And some might be critical actions that need a very fast, tightly constrained path with special policies around them. That is the broader idea I want to explore. Not just retrieval, but retrieval under constraints. Not just answer, but policies. Not just language, but language connected to a stage, urgency, and control. So in the future version of this project, I want a system to be able to gather information about the rocket, understand what kind of request is receiving, decide what policy should apply, and respond in a way that matches the urgency of the moment. Because again, if the rocket is failing, recovery is not just another query. So what I am showing today is the base. The simulation is working, the learned controllers are working, the runtime loop is working, the voice interaction layer is working, and now I also have new experiments like moon gravity showing that the system already has some interesting behavior beyond the original training setting. What is still ahead is the retrieval layer, the policy-aware common system, a live state-aware RAG behavior, and the deeper architecture I already want to build on top of this. So now that work has a real environment to live in, and that is why I wanted to make this video. This is the foundation. I'm looking forward to show you the next stage soon. Thanks for watching.